as per QS ranking. It's within top 400, if I remember correctly, in international ranking. So it's one of the very top universities. And Professor Askar also belongs to this university. So Dr. Assel will speak on heat and mass transfer in frozen soils, which is a very interesting topic, I think, for Belt and Road countries. So with this, I would like to welcome Dr. Assel to share her presentation. Yeah.
So good day, everyone. Let me tell some information about myself. This research prerequisite started since I was conducting research on de-icing chemicals at Kazakh Academy of Transport and Communication. That's why, and I used laboratory facilities of Kazakh Highway Research Institute. That's why I included the logo of this. Then I completed my PhD research in Brunel University, London. So the laboratory study of this research was continued in Brunel University facilities. Therefore, I included the logo of Brunel University. And nowadays, I'm working as a postdoctoral fellow on this topic of heat and mass transfer in freezing soils under the supervision of Professor Askar in Eurasian National University, and my affiliation is Eurasian National University at the moment. That is briefly about myself. So, okay, yeah. Shortly about our country. Kazakhstan is located in Central Asia and Eastern Europe on the globe, and at the north part, like 48 latitude and north latitude and 68 east longitude coordinates. I think it is center of Kazakhstan. The country borders are Turkmenistan, Uzbekistan, and Kyrgyzstan at the south, Russia to the north, and Caspian Sea at the west part, and China, China's Xinjiang Uyghur Autonomic Region to the east side. So we have moderate continental climate with the exception of the south part, with average temperature around -15, -20 degrees, occasionally dropping to -52 degrees Celsius in winter, and hot, dry summers, +26 degrees at the average, and raising up to +40 degrees in summer. The seasonal, so we have snow and we have frosts in winter. Seasonal freezing depths of soils in Kazakhstan. Here is our capital Astana, previously called Astana, nowadays is Nur Sultan. And the freezing depth in our capital is around 2 meters, 30 centimeters. That's why the mass transfer during the freezing is really important in our construction. We have snow storms occasionally. This photo was taken 28th of January of 2020, last year. It might reach to 2 meters, and we usually use plugging and cleaning from snow of our highways. But it's not so awful. It's not very often, but occasionally we have such kind of weather. So today we are going to talk about the frost heave, and before dragging you deeply into the physics, let me just briefly introduce you with frost heave. So frost heave is an upward swelling of soil during the freezing condition caused by extension of the water, and also by movement, by the transport of water from the unfrozen part to the freezing front. So this water segregates and construct lenses which make the frost heave deformations. So uneven settlement from frost heaving cause deformation of the structures and buildings. And here you can see one of the example of this deformation. And another thing, we usually treat our highway surfaces to prevent the slipperiness on the pavement. We use de-icing chemicals. During this winter, around 1,140 tons of ice melt de-icing chemical were used in North Sultan, and annually, depending on the weather condition, on average, 30 to 35,000 cubic meters are used of sand-salt mixture. Eventually, while this, while this snow is flagged, it eventually deposited on the roadside of the highways. And according to the study of our colleagues from Norway, Finland, and Canada, we found out that the amount of the chemicals deposited by roadside area, it's definitely higher next to the road and lower, but it's up to 40 meters aside from the road. So all these treated de-icing chemicals during the cleaning deposits on the roadside soils, and then it's just eventually dropped down by the time. However, we have some thoughts that these de-icing chemicals might not just drop down. We know that frost heave extensionally happened under the pavement because due to the high density and high thermal conductivity of the pavement material. So temperature of the pavement is much lower. For example, if the temperature of the pavement would be -20, the temperature of the ground beside the road would be -10, 15 degrees Celsius. So due to the temperature change, to the temperature gradient, the moisture is always moving from warm side to the cold side. So we have some assumptions that these de-icing chemicals might migrate directly under the pavement layers. That is why this research was conducted. Due to the frost heave happened on the under the road, under the highways. In springtime, we meet such problems as pavement failure. So it might be surface layers, or it might be just caving of the subways. So today we wanted to stop a bit, not too long, on the evolution of the frost heave theory. So frost heave theory actually started from Tabor in 1930, and it was developed by Everett in 1961, when he just used 2 cylinders and connected them by the tube. While freezing the top cylinder, the water was replenished the ice, and the ice was growing at the top cylinder. So that's how people understood that in open system, so it means there is a source of water, the ice is growing up and case a frost heave. The next model was rigid-eyed model of regulation or regulation theory by O'Neill and Miller. They made an experiment with ice, box of ice, and placed a wire loaded by two sides and on the frozen cube of ice. And notice that by the time the ice, the wire traveled through the frozen ice under the load effect, so the load impact. So the ice molecules were melting underneath the wire and refreezing back after this wire was moving down. So refreezing above the wire. This meant that frost heave and freezing directly related to the pressure and loading. The next one was semi-empirical model of Conrad and Morgenstern, who explained the water influx as a proportional empirical model proportional to the temperature. This proportion he called as segregation potential. And this theory didn't explain the physics and phenomena of the frost heave. However, it just showed us the formula correlation between the water influx and the temperature. The next one model was presented by Mikhailovsky, expressed porosity rate function. It's similar to this semi-empirical model, but here he correlated, he referred to the porosity rate. So the more air voids we have got in soils, the more frost heave we achieve. It also didn't consider the physical forces like surface tension, like cryosuction. It just considered the starting point and the final point of this process. The next model, hydrodynamical model, mass and energy balance with cryogenic suction determined by Clausius-Clapeyron equation, characterizing a phase transition of a single constituent, I mean water. So here we have got Clausius-Clapeyron equation, which is very correlated to Darcy's law and hydraulic conductivity coefficient lambda. However, yeah, this works only in positive temperature. Why positive? Or it might work actually in sub-zero, but the water should be in a liquid condition. So this model is working on moisture transition while it's liquid. That's why it's a bit under question how it's possible to move move the water in sub-zero temperatures while everything is frozen. The next one, frost-TB model, was conducted by USA Army of Cold Region Research, and it considered the element as discrete, as a mesh of discrete elements, and the heat over here was considered as like in a single cell. The amount of heat which is needed to turn all the water inside to the ice, the dark blue, is equal to 1. So by the proportion, how much heat used in these discrete elements, they found out how much water is in a liquid state and in an ice state. It's amount of water in soils, elements in soil mesh. So each mesh represented the proportion of ice and liquid water. Here this work would be explained by placing lots of temperature sensors into the tested soil sample, and then it's possible to measure how much water is in unfrozen stage and how much is in ice condition. I actually like this model. It's good for numerical calculation. However, it again doesn't explain the physical phenomena of the frozen ice and frost heave itself. The next one is kinetic model for fully saturated soils conducted and going on in China nowadays, I think in Tibet Research Institute, and they're considering the energy which is required. This model is very good, but it's working only for fully saturated soils. And what about when we have caves? Because previously we were told that porosity, that means air void, is increasing the frost heave. So in fully saturated soils, this model doesn't work. Therefore, we have the further research aims to study. First of all, we needed to examine the heat and mass transfer, and we just got an application as highway subsoils because it's the most vulnerable element in construction, because for building construction we use piles, which is below the freezing front, while in highway construction we need to layer the pavement which is above the freezing boundaries. So we firstly considered how this effect of de-icing chemicals actually affect on the frost heave. So study temperature and moisture distribution during slow freezing. Slow freezing is very important. It was dispute in January meeting of the Technical Committee 216 ISCMG, because many countries are using different test methods, and they are still disputing what kind of they wants to come to a single method of testing of frost heave, and the slow freezing gives us the maximum rate of the frost heave. So we decided to do it very close to the natural condition. Second, to study how de-icing chemicals affect the frost heave itself, and if they move, if they migrate from the roadside soils under the pavement. The next one is the role of vapor, because no one considered moisture exchange in a gaseous state. And the last one, we wanted to make a conceptual model of frost heave with vapor constitute. So by the time, the most precise and possible way to study this frost heave was a laboratory testing method. So we decided to increase the height of the samples. Usually there are, in ISDM, there are 15 centimeters, in European standard around 15 or 20 centimeters. In GOST, it's also just a small height of the sample. We decided to increase the soil sample up to 1 meter to make it as close to the natural condition as possible. This, they were supplied by Marriott bottle clean water, de-icing water. So we did several tests actually, tests. We did 5 tests. The first one, we supplied it with clean water, deionized water. The second test, we had supplied it with de-icing chemical solution. already. However, the soil samples were unsaline, so it was just pure soil samples. Then the chilling, the cooling was by these chilling collars by the temperature control bus, and the temperature and moisture and linear movement was monitored every 30 seconds by computer. Actually, the temperature was monitored because there were inserted thermocouples every 10 centimeters. So 10 centimeters, 10 at each, and plus the thermocouple on the chilling collar and the Marriott bottle, which was 4 degrees plus 4 degrees. We had 105 thermocouples measuring temperature at a time. So there were 9 such samples, 9 samples in a huge environmental chamber. So we designed the environmental chamber. This is facility of Brunel University. This is a handmade cool supply. So it's actually the liquid which is frozen up to minus temperature and provides the cold. There are vertical linear gauges connected to the plastic rod and to the surcharges on the top of this sample, chilling collars themselves, thermal insulation between. Test design looks like this. This is the cooling unit. So this is how we cool down the temperature at the top with vertical linear gauge. I just showed the valves so that the flow might be regulated and the temperature would be the same at the top, at all 9 columns from the top. Here, I just showed that how it looked after dragging to minus 25 degrees Celsius. So to prevent the condensation on the top, I just placed a clean film on it. So no condensation might go inside, and inner surface was lubricated with with ointment with oil. Yeah, this is a picolog. 12 picologs were used and 105 thermocouples. This is the tube connected to the fridge plus 4 degrees and supplying it from the bottom, the sample from the bottom. So the physical and mechanical characteristics of initial characteristics of the soils are represented in this table. This is how the samples were made to provide the same density. The energy by hammer were calculated corresponding to the Proctor test, standard Proctor test by BS British Standard, and it was calculated for each cylinder. They were just like Lego element. They were assembled in these plastic collars were assembled one above one like a Lego, and the volume of each collar, it was 10 centimeter high and 10 centimeter in diameter. So there are required 63 blows with 2.5 kilogram hammer to provide the required density. So this is the way how it was just. So we divided by 5 centimeters layers and made the unified structure of the sample. So it's growing up and the colors are assembled. While after that, with clean film, it was properly hydro isolated and vapor isolated. And plus there was some latex colors the connection, so no water might leak out, so no vapor. It was absolutely hydro-isolated. There are 80 samples, and after it, there were cut into portion. The top and the bottom one cut in by each 1 centimeter. And here we got samples from the top and the bottom, so in between intersection of the colors. How we got the soil sample themselves? We just tried to make this sample as close as possible to the natural soils of Astana, and by density, by liquid and plastic limits, we just found out that the mix of the kaolinite and sand makes this very close, the properties, and by Proctor test, standard Proctor test, we found out the maximum dry density and optimum moisture content curve. Experimentally, we found out this curve, and we know that under the highways, the dry density, which is aimed to achieve, is 95 to 90% of the maximum dry density. So we got the maximum one, 1.9, multiplied it to 0.95, and got the desired density under the highways. So it was correspondent to the 17.3, 17.1, 17.3 moisture content. So we got these parameters to use as an initial for these soils. By direct shear test, we got angle of internal friction 24 degrees and cohesion by 10 kilonewton per meter square. We conducted several CBR tests, a series of CBR tests in triaxial rig. There is a surcharge on the top of each sample, and in our testing sample there is a surcharge which is equal to 3.5 kilopascal. This is the surcharge representing the weight of the pavement. So by California bearing ratio, we got that at 17%, we have got 10%, at 17% of moisture, we have got 10% of bearing capacity required. While at maximum level, at maximum, which one? This one, yeah, at 14 degrees over here, 14 degrees, or 14% of moisture content, it was 100%. So we got it as 100%. And while increasing the moisture by 17%, we got that it dropped from 100% to 10%. So initial bearing capacity was as a 10% by California bearing ratio test procedure. The temperature was decided to be cooled down by 2 degrees per day. So it started from 0 or just above 0, plus 3 degrees, and to initiate the freezing at the top by 2 degrees per day, and up to minus 24 degrees at the 12th day. So there were 2 freeze cycles traditionally conducted by all the countries. And totally it got around 25, 26 days. So the temperature was dropped, and then it led to raise, and then again it was dropped. And after this experiment, we were measuring how much water migrated or chemical solution migrated to the top of the pavement layers. So sampling after the freeze test, you can see there is a frost heave occurred at the top of the soil. And sampling was, as I said before, every centimeter at the top and 10 centimeters at the bottom side. So there are some frost heave observational results. This is with de-icing, no, this is with deionized water, so clean water, frost heave, and the temperature drop. So the first cycle finished, the second one, the temperature got even lower. However, the frost heave had, because the water which is dragged to the top required more energy to be removed, to be taken out, to cool down the soil. Therefore, because there were more water dragged. This is in the samples supplied with 11 gram or 11,000 milligram per liter. So the samples instead of water were supplied from the bottom chemical solution. And we see that the frost heave decreasing over here. It's obvious because chemical solution do not freeze at the negative temperature. And freezing less. We conducted several tests. This test is similar to the first. However, each of the sample had different density. So number one had the highest density, then it was lowering down till the loose soils. So we can see how the frost heave changed during the same freeze-thaw cycles. This test number 4 is similar to test 2. So the samples of different density, here is different density now, were supplied with de-icing chemical solution by 11 gram per liter. And here we got again different values of frost heave at the end achieved. In the 5th test, chemical solution was increased twice. To 22 gram per liter or 22,000 gram. So this is sodium chloride de-icing chemical. And we observed the temperature distribution by Picolog system. We can see here that the top temperature, zero temperature is going to almost to the bottom, but it's not freezing. The entire sample, so it's freezing around 85% or 85 centimeters of the sample. And in the second freezing cycle, it's not freezing at all because so much water was dragged from the bottom upward. That is why it was required more energy, more heat to be extracted to drop this temperature downwards. That's why it was completely different. While in the icing chemical solution, we can see the opposite figure, opposite picture. It seems that the sample was frozen completely. However, because it was de-icing chemical, it wasn't segregated. There are no ice. There were just negative temperature, and we can see that temperature dropped here up to -10, -15 degrees. This is sample 3 and 4 and 5, and the similar patterns we can see over here. And what is the results of these tests? First of all, I want to show you the moisture distribution over the lens. We can subdivide the entire length of the sample into several zones. The heaved zone, where the moisture was dragged in, so the desiccated zone, which supplied the heat zone. That is why the temperature, the moisture was less comparing to the initial moisture content. So it was decreasing up to 16% over here. And the zone which is supplied by water table. So here the capillary raise happened. That is why it raised. A bit different figure we can see here. The moisture was desiccated, but not so much, not up to 15–16%. Capillary raise was lower. It was just around, let's say, 20 centimeters from the bottom. Distribution of the dry density. Here we can see that while supplied with clean water, we can see so much change in dry density because of ice lands that were formed. Big ice lands, a thick one. And in supply with de-icing chemicals, there wasn't much change in the dry density. So the soil structure and ice lands looked like this on the cut. So well supplied with clean water, we could see around 2 millimeters length, yeah, ice length, and while supplying with de-icing chemical, there were just tiny microscopic lengths less than ½ millimeter. The bearing capacity changed directly to the moisture content change. So in the parts where moisture content were more, the dry density increased. No, moisture content was more, dry density decreased, and the bearing capacity dropped dramatically. While in zone of desiccation, they were increased. I don't think it was 14, it was around 16. So bearing capacity increased. So it was like layers of decreasing and increasing of the bearing capacity. What about the chemical content? Did it move or not? We conducted a test with electrical conductivity measuring apparatus, which was calibrated before. So this is a reference zero because this is amount of this is electrical conductivity at the initial stage of the soil, while these ones are after the salt was added. So we made a calibration chart first, and then found out that de-icing chemicals migrated to the sample over the all length of the soil. So this was initial one stage of electrical conductivity. I again want to repeat that is referencing zero, referenced zero. So it was initial stage, and we found out that the sample was salinized, so saline at the end. What does it mean? That means that the designed characteristics of the soil are changing by the time if we are treating them by de-icing chemical. So after a year or several years, there are no more design characteristics of the soil. There are saline. The movement of de-icing chemicals were explained. Why we actually researched this? Because there were controversial issues in different research. That some of them said that de-icing chemicals are not moving at all due to the frost heave. Some said it might move. However, we proved here that de-icing chemicals migrated up to entire length of 1 meter due to the cryosuction forces. If we consider here the film water, which is transported the de-icing chemical cations and anions, and then molecules of water eventually turn to the ice over here. However, we know that by the osmosis, the more chemicals we have got, the more water is pulled into that side because the osmosis force. So there are two forces affecting the sample during the frost heave. The first one is cryosuction and the second one is osmosis. However, cryosuction force is greater than osmosis. That's why the movement happened. And that's why it happened less comparing to the deionized clean water supply. So what about the water mass transfer here? And here I want you to look through these pictures. The first one, we can see the soil sample before the freezing. So we have got some free water, gravity water, some film water, which is always around the soil particles and it can't be moved out. And there might be some capillary water as well. So what happened over here? Let's imagine we have a closed system. In closed system, there is a phase balance always, and unless the system is saturated, the evaporation happens, the evaporation from the liquid phase to the gaseous stage. It happens till the system equilibrates. When it's equilibrate, the drying out or evaporation stops and system is in equilibrium. This picture is when the temperature is stable. The second one, when we have some freezing from the top. While we have freezing, some of gravitational water freeze. And because the film water becomes thinner and pressure decrease over here, we see that the water from the warm part start to migrate in order to replenish the pressure and the film thickness over here. So it starts to migrate upward. And due to the temperature, it freeze again. So we can see here that ice are growing, and what happened? It fills all the gaps. It fills all the pores over here. And by the time it fills, eventually a frost shattering happens. So a crack which provokes more movement of liquid water or vapor. We consider it vapor because it's not possible to move of the water over here because everything is frozen now. So, and gas may leak to the tiniest element of the soil, tiny bits of the soil cracks and fill it in. That's why we consider that mass transfer happening probably by the gaseous stage. Here I would show you another example. This is a vein, ice vein, showing how the water or liquid, or I mean the water molecules in gaseous stage were moving. So they formed first lengths by this ice vein, then occasionally it's filled out, the freezing continues, it's starting to fill the next length, and the frost shattering happened due to the thickness of this ice length. It just cracked and filled out with the gas, with vapor again. That's how it happens. So I wanted to say that classically we thought that only two phase is in charge in the frost heaving. However, there are three phases are in charge. That we wanted to say. So the water firstly turned to vapor, and this vapor migrates to the place with negative pressure, and then it might go to the water and ice stage again. And sometimes water stage is so quick, so it just solidifies from vapor to ice due to negative temperature. Oh, sorry. And the calculation of it, the equilibrium between the water and vapor phases in porous medias is can be represented by this formula. So amount of water, depending on the pressure and temperature, is in the equilibrium with vapor, depending on the pressure and temperature. However, this happens when the temperature is constant. Again, if it's not constant, if one side is cold, the second side is warm, it's provoking the movement, initiating the movement. The mass of vapor can be calculated by the known formula in physics, where the nu is the molar mass of vapor. P is a saturated vapor pressure corresponding to the temperature. And I told before that pressure is always tries to be saturated, because if a system is unsaturated, the evaporation continues. So it stops, the drying out stops when the vapor is saturated. This is the volume of the air in the soil. Universal gas constant is equal to 8.3, and temperature in Kelvin. So we can calculate the mass of the vapor in the closed system. We know from the classical soil mechanics that amount of soils, how to calculate amount of soil particles, mass and weight and volume of the liquid part, and we know how to calculate the volume of the gaseous stage. We just turn it into these vertical tubes, just to transfer it, to calculate it. So this is the same. We could find out the volume of these three parts of these three phases. We just turn it by knowing that form of volume of cylinder is equal to PD squared to the H, and we can easily transfer it to the cylinders. So we got a channel now. We got a cumulative channel of the air of the gaseous stage. And the volume of vapor passing through this channel is equal to the velocity, to the time, and to the diameter of this cumulative air voids, this cross section, actually. So it's possible to calculate how much moisture is moving through the soil. It's possible to predict it. It's possible to explain it by general physics. Calculation of the vapor rate passing through the cumulative air voids is counted as mass of ice built in a certain time when the temperature is known is equal to density of the vapor and volume of the air voids. So we're just turning the air voids. We said before that volume of the air channel is equal to density, velocity, time, and cross-section over here. So here we can just calculate the mass of ice built in a certain time. And this was the novelty, actually. It was an application which is possible to turn all the knowledge we did before. And here the difference from the previous knowledge, that we do not use Darcy's law, we do not use hydraulic conductivity, because it's impossible to move for water in a liquid stage in the freezing media. It might move in very tiny amount by the hygroscopic films, by the hygroscope. Only hygroscopic water can move. All these transfers happens by vapor, by gaseous stage. And the results of this work regarding the de-icing chemical mass transfer were published in 2021, this year, and previous year in Cold Region Science and Technology and Transportation Geotechnics. The vapor mass transfer model is going to be presented soon and published as a manuscript is prepared. The algorithm of vapor flow calculation in unsaturated soils using the presented with fundamental thermodynamic equation was presented here. And the testing method was developed by slow freezing and increasing the length of the sample. There are some new questions for the new upcoming doctoral students if they want to work on. And there are some interdisciplinary laboratory research to consider. At the moment, we are working on the in situ tests possible to prove or to consider the frost heaving process in Nur Sultan. And my long presentation is over. Thank you very much. If you have questions, please welcome. It was so long, probably so difficult with physics. Sorry.
Thank you, Professor Assel. The presentation is very interesting. Actually, in Nanjing University, we also have done some monitoring, especially field monitoring about frozen soil. So yeah, I think we can have, in the future, we can have some collaboration.
I hope so, because I'm in daily monitoring of the Chinese researchers who are just very close to my pattern, but still not using this method of calculation. Thank you.
Yeah. Any questions?
Dr. Assel? Maybe Professor Askar can ask.
Such a lot of information, probably too much. It's a bit fundamental research.
Please, Dr. Ankit, maybe you have questions.
Dr. Assel, are you doing any field experiments on your?
We are considering some field experiments now by monitoring and considering the bearing capacity of the of the foundation in the frozen media. That is how it's going to be related as it's full in situ tests. But for vapor, it was mass transfer in a gaseous stage. The laboratory design test was more preferable at the time. But nowadays we are working, yeah, at the field research, which would be presented later.
Okay, yeah.
Dr.
So
Assel, I have a small question. Yeah. In my research about frozen soil, I think the phase change mechanism is the most complicated process. In your research, how can you investigate such phenomena? Do you have any new findings?
The calculation of the moisture transfer in a vapor stage, that is my contribution to the general knowledge. There are some new findings how to calculate the hygroscopic water movement by Chinese researchers nowadays. So I think if we join these two components of vapor in a liquid stage in hygroscopic water, there will be a complete puzzle of full explanation of the physical phenomena in the freezing soils.
In laboratory testing, I think many factors can be controlled very easily, but for few tests, I think there will be some differences. Can you give any interpretation of the difference?
So what I think to be needed to continue this, to conduct this test in the field, there are thermocouples, which is measuring the temperature. We need probes of moisture. So sensors of moisture, which is registering the water in a liquid stage by the time, and something to measure the level change, so the frost heave itself. So yeah, that is the thing which is needed to conduct the in situ field experiments. And a load, yeah, a load, sure, surcharge.
So I have some comments, Dr. Chu.
Yeah.
Can I give some comments?
Yeah.
So my comments is, you know, is Dr. Assel is now very active, and she will organize already fixed time for organize of freezing committee, frost committee, technical committee, some workshop in June, beginning June. So I think it's better. So you can, if you want to join this workshop, so Dr. Assel can sharing and send some information about papers, instructions, and also you can send paper because the deadline, I think 15 May, right, Assel? Dr. Assel, 15 May.
Yes,
15 deadline.
15th May, technical committee 216 of ICCMG.
So you can send to Dr. Ankit and to Dr. Ju and some another participants from these webinars, maybe until 15 May, these people can last chance sending paper. Dr. Assel.
Yeah. I will try.
Mm-hmm. It is interesting because we have very near China, Kazakhstan, we have same boundary, but not so deep communication.
Yes.
So sometimes surprising. Why then?
Yeah, we should have more discussions.
Yes.
Although it now in China we don't allow foreigners to come to China now, but we can have some internet communications.
Yeah, that would be safe.
Yeah. And I'm very glad to find the laboratory testing equipments in this presentation. I think it's very wonderful.
Thank you very much. Yeah, the laboratory facilities, I want to repeat, they are in Brunel University, London, at the moment, because we use their facility. However, it's possible to do it here, but we have got already the results of the laboratory testing. So it probably would be more interested if we continue in situ.
Yes. In China, let me introduce briefly about my work related to frozen soil. Actually, yeah, from my PhD study in Hong Kong, we start to use fiber optic sensors to monitor different parameters of geotechnical infrastructures. So I think in the since 2015, we start to use the optical fiber sensors to monitor the moisture distribution in ground soil. The technology we use is called actively heated fiber optic technique. So we can install the optical fiber sensors in the ground. Then we will heat them, and we can monitor the temperature change in the optical fiber sensors. Then we can back calculate the moisture of the ground. And my student Wu Bing, she tried to use this technique to monitor the behavior of frozen soil. So we have done several laboratory tests to study the relationship between the temperature change and the ice content of frozen soil. And the relationship is very good. So after that, we installed the optical fiber sensors in different places in China to investigate the feasibility of such technique to monitor the moisture variation and the ice content of frozen soil in winter time. Yeah.
So Dr. Zhu,
yeah.
we must be, I think, is improve of technical freezing committee 216. Usually inside of member from Norway, from Sweden, from Finland.
Yeah.
Sleeping well there, like freezing people. You know, sleeping, not active. So why is Dr. Assel beginning to reactivate of this technical committee, maybe together with you, with Chinese and Kazakh, because you know Scandinavian people is freezing people, they're sleeping forever there. Not wake up.
They are very good. They do send some presentations now. I can't say that Scandinavian are frozen, but you would be very welcome.
Okay.
Very interesting, and I just probably later I would like to learn more. How do you find out the moisture content in the frozen soils in the liquid stage and frozen stage? So probably later on I would be happy to discuss this question with you regarding your research.
Is there any other questions? If no,
maybe
I
from
think
students. Maybe from students.
Oh,
we
students.
have some students from Kazakhstan, from Russia.
Oh, okay.
So we have a very big group from CIS countries, especially from Kazakhstan and Russia. So please, students. Elena here from Russia? Elena?
Yes,
Braga.
I'm here.
Yes, well, you must, Tyumen is one of Siberia, South Siberia. You must to have some questions to be active, please.
No, I haven't questions.
Questions, okay. So anyway, you know, we have several PhD students here, not only from Russia, also from Kazakhstan. So why I also want to reactivate from Kyrgyzstan, Dr. Gulzat maybe also has questions. No questions, huh? Okay.
Okay, then I think this will be the end of the presentation. Thank you, Dr. Assel, for your wonderful presentation. For the next week, we will have, I think, 3 webinar presentations. I look forward to seeing you then. Thank you very much for all your participation in this webinar. Thank you.
Okay, thank you very much for listening.
Thank you, Dr. Assel. Thank you very much.
Physics.
Very good presentation.
Yeah.
Thank you. And bye-bye.
Bye.